the radius of gyration is L times into the nu. And then there are some prefactors here. So this nu and this L, right, gave chemical details of polymer, solvent.
Hello.
Yeah.
Could you share us your screen? Yeah, okay.
So far we have been discussing a single chain in a solution, infinitely dilute solution. And what we found is radius of gyration in general is, of course, determined by Kuhn length in our modeling. And that depends on the chemical detail of the polymers. And then it depends on molecular weight, degree of polymerization with an exponent nu, which also depends on the chemical details, flexible, semi-flexible, and also polymer condition, polymer solvent conditions, a good solvent, a poor solvent, etc., theta solvent. And then the prefactor here, that number gives the proportionality between radius of gyration and the molecular weight power, this exponent, in terms of the various parameters of this description of a polymer and solvent, like excluded volume parameter, three-body interaction term, persistence length, etc. So this is basically the summary of what we have been doing so far for a single chain. Now it turns out that this result is an important foundation. We'll be using this result again and again. So given a particular condition, good solvent, you know what the value of nu is. If it's a poor solvent, you know what the value of nu is. If it's a semi-flexible chain, you know what the value of nu is, right? What the crossover is, right? It doesn't have to be 1 or 0.6. It could be anywhere in the middle effectively. And that depending upon, right, that depends on what the semi-flexibility is. Or if the polymer is charged, it could be something in between. Right? From now on, what we are going to do is to look at the two important variables, experimental variables. As you know, one is the temperature. The other one is polymer concentration. So far, what we have been working on is, when I say single chain infinite dilute solution, I'm looking at something here. This is where we have been studying so far. Isolated chain in infinitely C concentration is essentially 0, infinite dilute solution. And somewhere here is, say, theta temperature. Right? And we looked at the single chain at temperature higher than theta, the single chain at temperatures lower than theta, right? So from now on, we are going to go in this direction. We are going to go into increasing concentrations. And then along with that, we will also study the role of temperature, go up and down. So that's what we are going to do. But today I'm going to be in the regime of temperature higher than theta. So I like to look at this region. That's what I want to look at. That's my goal. Once we have an understanding of this system, which is a solution, polymer solution, not necessarily infinitely dilute solution, but it's a solution, I will describe in quantity terms what the solutions are, how we are going to characterize them, right? And then eventually maybe 2 lectures down the road, we will talk about the significant role of temperature. And then we will also explore questions like when such solution is stable. Now, under what conditions the solution becomes unstable? These are the kind of questions we are going to address. So this is our roadmap. This is our immediate goal. So to begin with, let me consider very close region somewhere here. I mean, the infinite dilute solution. So I'm somewhere here to begin with. Okay, that would be dilute solutions. In contrast, here I would say infinitely dilute. This is an infinitely dilute solution, namely a single chain is alone, right? It's far away from every other chain in the system. And today we are going to talk about dilute solutions. And what I will do is, maybe I should send you, Junfang, are you there? I should send you the PDFs to help you guys, all right? Let me send it to you now. Okay. So what I like to remind you is in your elementary courses, high school, and also undergraduate programs, right? Consider, for example, a gas. Suppose I have a box filled with the gas molecules. Okay, there is one gas molecule, another one, another one, another one, etc. Let's say the radius of that gas molecule is R. Then you know from equation of state of a gaseous state, pressure divided by Boltzmann constant times temperature is equal to N over V. Because in this box, there are N molecules in volume V. We know that, right? This is a very elementary study, right? Pressure, ideal gas law, pressure times volume is NKT, ideal gas law. This is when there are no interactions. This is extremely dilute condition, infinitely dilute gas, right? But now when I add more and more molecules into this volume, then what you get is higher order terms. There will be a term which will go like square of this, N over V square, for example. Because this molecule is interact with this, then the pressure will depend upon this intermolecular interaction, N over V square, and then there's a prefactor here, right? We can compute this. And if you go back and look at your earlier notes, that prefactor, let me write it to be A2. A2 is the second virial coefficient for this gas. Then I have higher order terms, namely cube of N over V. And then there will be A3, which is third virial coefficient. The important thing to remember is this A2 is proportional to there is a number there which we are not going to worry about. It is proportional to volume of this molecule. It will go like R cubed. This is, we know, this is for a gas, for a gas. For a gas, we know that pressure by kT is N over V. N is a number of molecules, right? So the number concentration. So don't get confused with the degree of polymerization. This is the number of molecules, right? And then here, number of molecules by volume squared. The prefactor is second virial coefficient. That is proportional to R cubed, radius of this gaseous molecule power 3. So what we do is, you could do a proper theoretical calculation. For polymer solutions, we'll copy this result because you can derive it exactly. For polymer, for dilute polymer solutions, I'll draw a figure once more. And I have a chain like this, another chain like this, another chain like this, another chain like that, right? And radius of gyration is Rg. There are N chains in volume V. So the pressure that I wrote down here now becomes osmotic pressure. Osmotic pressure. Let me write the letter pi for this. So copying that answer, I have pi over kBT is equal to N over V plus N over V squared, A2 plus etc. It's exactly what I wrote down here. Now this becomes osmotic pressure at that temperature. N over V is number concentration of the polymer chains, and N over V square is square of the number concentration of polymer chains, and that's the second virial coefficient defined in this notation. And that goes like R cubed. So now in this particular case, A2 goes like Rg cubed, because Rg is radius of gyration. Okay. But now in our polymer community, we define polymer concentration as the following. We don't define N over V as a polymer concentration. We define polymer concentration C is defined to be number of chains times the molecular weight of that chain divided by volume. Right? M is the molecular weight. That's the way we define polymer concentration. Therefore, we go back to this equation. We really write to be M over kBT is equal to N. Okay, let me write, to make it easy for you, I write 1 over M, N, M over V. How about that? Because this factor of M cancels with this factor of M, so I'm writing N over V like 1 over M times N M over V. Plus A2, right? Apart from numbers, right? I would write Rg cubed. I'm not writing the prefactors. Okay, A2 goes like Rg cubed. Then I want to write N M over V squared, but I have only N over V squared. I put M squared there, they have to take it down M squared here. And then plus higher order terms. Right? This M cancels with that. That M squared cancels with that M squared. So I have exactly the same equation as this. And then A2 I have written to be Rg cubed. So therefore, I could rewrite this to be pi over kT, 1 over M, C, because C is our polymer concentration, plus Rg cubed by M squared, C squared, plus etc. Therefore, I could rewrite this to be 1 over m c plus, let me write capital A to c square plus etc. Where capital A2 is equal to, proportional to Rg cubed divided by m squared, right? This is my A2. A2 is this factor, Rg cubed by m squared, that's what it is. And we know this because we have this important relation. Rg goes like n per nu. N is proportional molecular weight, as you know, n per nu. Therefore, the second virial coefficient goes like Rg cubed, that is molecular weight power 3 nu divided by m squared. Therefore, this goes like a molecular weight power 3 nu minus 2. So we get a very clean expression for second virial coefficient in terms of molecular weight. Okay, so that's my osmotic pressure. So let me rewrite this once again. So we get for our case pi over kT C over m plus A2 C squared plus etc. Then the osmotic compressibility is d pi, let's unit in units of kT by dc. So that is 1 divided by m plus 2A2C plus etc. Therefore, this offers an opportunity to explore experimentally. This equation is such a simple expression, but it gives us a very important possibility, significant possibility to measure things experimentally. For example, if we were to go and make measurement of osmotic pressure of this solution, I have a polymer solution, measure osmotic pressure at different concentrations, then you find the derivative or slope of that expression, you measure it, and then find the compressibility, d pi by dc. And if you plot d pi by dc as a function of c, the intercept would be molar mass, and the slope would be second virial coefficient. So if I take this, and then I plot this as a function of c, right, I will get a straight line here, and then that intercept is 1 over m, that is I'm plotting this quantity. And then the slope will give me second virial coefficient. Second virial coefficient for molecules. Please remember, when we described the single chain extra volume effect, we defined the V, extra volume parameter V, as a second virial coefficient between segments inside a polymer chain. Here, this capital A2 is second virial coefficient between different chains. That is, how does this chain interact with another chain, a whole chain, how do they interact? So that's a distinction between this second virial coefficient, and similarly, you can write third virial coefficient. That's the difference between this capital A2 and the little v that we talked about before. Okay, so this is an experimental protocol. But it turns out in modern times, there is a much better, a very simple technique. Modern times means I'm talking about 50 years, 70 years, compared to classical methodology of measuring osmotic pressure. It is still very difficult to measure osmotic pressure, but we had heroes, a century ago, when they were able to make very accurate measurements of osmotic pressure. The way we do that is going back to our scattering technique. It turns out, as you know, in scattering experiments, I of k, remember scattered intensity I of k, this is proportional to structure factor S of k. We know that, remember that, recall. Right? Scattering intensity is proportional to structure factor. Now, one can show right? This S of S, when the K going to 0, that is, you measure the scattering intensity at a different scattering wave vectors, but you go to the thermodynamic limit. When K is equal to 0, you remember K. K is reciprocal of observational length. When K goes to 0, your observational length becomes infinity. That means you are looking at the whole system. That means you are able to look at the thermodynamic properties of the whole system, not a single molecule. In that limit, I can show that this is exactly equal to 1 divided by this quantity, d pi by kt by dc. Can show, right? There are very good names for this expression. It's called sum rule, but let's not worry about the nomenclature. The important thing is, if you measure the scattering intensity and then you extrapolate to k is equal to 0 at finite concentrations, we are not doing single chain in the c is equal to 0 limit, right? For finite concentrations, you measure according to this expression, this is related to this quantity. That means I can use this expression. Okay, I can use this expression to understand from scattering measurements to know about the second virial coefficient. And right, you already know that you can get molar mass from single chain measurements, the extremely dilute solutions. In extremely dilute solution, the C is 0. C is 0, right? We're almost 0. Therefore, this is not important. Therefore, you get 1 over m. Therefore, this tells me, therefore, if I plot 1 over yes, k is equal to 0. I'm sorry. K is equal to 0 as a function of C, because 1 over S of K is this d pi by kt by dc, right? I'm taking reciprocal of this, therefore I'm plotting this quantity. At a different, at a finite concentrations, what you get is you get something like, let me use some color code to make life easy. So here is one data point here, another data point there, another data point there, another data point there. So you extrapolate this to 0 concentration, that will give me 1 over molecular weight or 1 over n, depending upon the definition, the contrast factor definition. It's a 1 over molecular weight, 1 over degree of polymerization, depending on the units there, right? So that's the intercept will give me 1 over m, and the slope will give me second virial coefficient. Slope gives me 2 times A2, right? This is the intercept, that's the slope, 2 times A2, but that gives me, from there you can get second virial coefficient. When I put an arrow like this, it gives me, I'm not telling it is exactly A2. The slope is exactly 2 times A2, but this arrow tells me that I can get A2 from this. Okay. So this is going back to this situation. But we also know this situation. For infinite dilute solution, we know how to determine RG and how to determine M. That's what we did so far. So what I like to do is I like to combine the methodology that we used here for infinitely dilute solution here, and then what we just argued for K is equal to 0 limit. This result. I'm going to use the previous plots, but let me remind you, right? For infinite dilute solution again, recall for infinitely dilute solutions. We had 1 over I again, I of K, and he had K square, which we wrote it to be sine square theta by 2. Right, remember that? Then we will have a data like this. Oops. I don't know what's happening there. Oops, sorry. Okay. We had data like this, straight line, and then we had an intercept, that was 1 over m, 1 over n we had, but in our nomenclature now it's m, and then the slope it gave me Rg, right? In fact, it was Rg squared by 3 times molecular weight. That's the slope, but from there we can get Rg. So this is for C going to 0 limit, right? This is what we had. For infinity dilute solution, that C going to 0 limit, and that's what we had. So what we are going to do now is we are going to combine this figure with this one. Because practically speaking, you cannot make a measurement at C is equal to 0. You cannot, because if C is equal to 0, you don't have polymer, you have only solvent. You cannot measure this. So you have to measure it only at some finite concentrations, right? And then theta you will vary. So you make measurements at finite concentrations at different angles. So we'll put these things together. If we do this, right, we get what is called the Zimm plot. We got Zimm plot. How do you do this? Oops. We do that with, again, let me draw. This is one over I of k, or I can put even, within the prefactors, everything, 1 over S of k, which is proportional to 1 over I of k. This is experimentally you measure I of k, and that is proportional 1 over S of k. This is what I'm going to plot. So let me pick a concentration, some concentration, right? And then I have data like this. I have one data point here, right? This is at one angle. So here I'm going to plot sine square theta by 2. Okay, I'm going to plot versus this. This is one theta. And then another theta, I change the angle, then I get to say something like that. Another one, say something like that. Another one, say something like this. This is for C1. Okay, this is at one concentration. At a higher concentration, let me do C2, another higher concentration, but it's still dilute solution. I will have for this angle, I'll get some number, right? And that number will appear somewhere here at this point. But in order to do the extrapolations correctly, namely, I want to extrapolate concentration going to 0 in one limit, and I want to say K going to 0 in another limit, right? K, that is theta is equal to 0 in another limit. So I'm going to displace. I'm going to write this to be C, that is concentration, and I'll put, say, something like some factor to make the plot look better. Plus, say, I don't know, A. Right, A is some number, so that I'm going to displace it a little bit, right? Or I can put A, if you like, I can put it any way you like, right? Plus, I can put A here to adjust the concentration a little bit. So, or the angle, depending upon how you do it. If you do that, you are going to displace the data a little bit higher. The data is here. So now it will look like this. One, another angle, third angle, and fourth angle. This is for C2. Okay, and on and on. And then for a higher concentration, I'll have something like this, something like that for C3. So what you have is you have series of data which will look like this, which will look like that, which will look like that. This is one concentration, another concentration, and these are at a different angles. So this is a theta 1, this is scattering angle theta 1, and this is theta 2, so this is theta 3, and this is theta 4. I'm illustrating here with the 4 scattering angles and 3 concentrations. Based on these data, then you can shift the shape of this curve by playing with this constant A. You can make it more slanted or less slanted by choosing a particular value of A. You have to play around. Right? But what we are interested in is given this kind of a description is let me consider C is equal to 0 limit. When you consider 0 limit, then I will go, I extrapolate these data. So what I will have is, when I extrapolate this, right, I'm going to extrapolate them to 0 limit. So that is an extrapolated quantity. That's an extrapolated quantity. That is an extrapolated quantity. Okay. This corresponds to the C is equal to 0 limit. So I have an extrapolated values of the scattering intensity at the different angles at C is equal to 0. In a similar way, because I'm interested in this picture, I'm going to extrapolate for theta becoming 0, K is equal to 0. So when I do that, okay, I extrapolate this, right? I extrapolate that one, and then I get something like that one, and extrapolate this one, right? Something like that one, extrapolated this one, something like that one, right? Something like that one, like that one, like that one. These are extrapolated. So then what I have is I have equivalent of this curve, which I'm going to draw like this. Okay, and I have equivalent of this curve, that is as a function of C, but the K is equal to 0. Then when I do that, I'll get curve like that. Then what you get is something correct, right? Now this means you get this intercept, because the intercept here is right as 1 over m. When I look at this curve, as you know, as 1 over m, and here also it's 1 over m. So if you do your measurements correctly, you should get these 2 intercepts to be 1 over m. And from this red extrapolated line, you will get Rg. This will give me measurement of Rg. And this one will give me second virial coefficient. So in one experiment, right, at finite concentrations, dilute, and different molecular weights if you wish, we get molecular weight determination, Rg, and A2. All 3 of them come about, coming from this Zimm plot. Okay? So basically, I'm summarizing here, what we have managed to do is to combine the known result here that we built so far with the expression that we got for dilute solutions, and using this thermodynamic law, right? Using this thermodynamic law, we are combining this picture with this picture to give me this Zimm plot. Now, this is a very important technique used in polymer science, constructing Zimm plot from scattering and then measuring these 3 quantities. But I hope all of you will make these measurements, because this is the measurement is easy, analysis is hard. It needs a very good understanding of what is going on into interpreting these results. Okay, so that's a Zimm plot. Now, what I like to do is I like to introduce some other related plots. Okay. We also know, right, based upon single chain behavior, we also know the scattering intensity going back to this result, for example, even this result, right? I could rewrite this to be I of K is equal to I of K is equal to 0 times 1 minus K square or G square divided by 3 plus etc. And you know the condition for K times RG is less than 1. This is again going back to the device structure factor, right? I'm repeating myself, right? I of K, if the solution is dilute and I of K at some scattering angle related to RG, if this condition is met, scattering intensity is given by this formula. So let me take the logarithm of this. If I take logarithm of this, log of I of K is equal to log of I of K is equal to 0 plus log of 1 minus K square RG square by 3 plus etc. Right? Logarithm of a product is sum of logarithms. So that means that this is equal to logarithm of I of, I'm sorry, I made a mistake here. I of K is equal to 0. And when K times RG is small, right? If this is small, then logarithm of 1 minus X is minus X. Okay, this becomes minus K square RG square divided by 3 plus etc. Only if this condition is met. All right, otherwise we cannot make this approximation. If you are in this situation, right, then if you plot a logarithm of I, scattered intensity at some wave vector K, at same vector K, if you plot this as a function of K square, and you know what K square is. K square is sine square theta by 2, 1 over lambda incident wavelength, right? 1 over lambda square sine square theta by 2. If you plot this, you will get a straight line. Because, right, this is y is equal to slope x is K square plus some constant, right? So you'll have something like this. If you normalize this, then it'll start with 1, right? If you bring this to the left-hand side, then logarithm of I of K divided by I of K is equal to 0, that will be 1, right? When K is equal to 0, that will be 1. So in general, if you plot like this, the slope will give me RG. This is called the Guinea plot. This is same as the device structure factor that we had. In general, for small angles, right? Small angles, we argued that this is the case. Structure factor, it goes like this one. In that particular case, we had here N, capital N, right? But that goes into, because there are so many of scattering centers, therefore the intensity will go proportional to the scattering centers. But if we can normalize this in general, and then you get RG from this Guinea plot. The other plot that I like to do, which we already know, is called a Kratky plot. We have already discussed this, but let me remind you again. In the other limit, so instead of, right, this is for here. For the other limit for K times RG greater than 1, right, in the other limit, opposite to that one, we knew that I of K is proportional to 1 over K to the fractal dimension, 1 over nu. We know that. Okay, that means if I plot, this means if I plot, suppose I plot as a function of K, and here is my I of K, and then K power 1 over nu, right, 1 over nu, then as you know that it will be flat. Because I of K times K to the 1 over nu is a constant. It will be flat like this. For small values of K, since I'm plotting something with the small values of K, it will go like this. We talked about this, right? It will go like that. So normally what people do is, they don't write 1 over nu. They write this to be, say, some number A. Let me write down with a different color. Maybe I'll write A, Ka, and you collect the data. You collect I of K, and you know K. Then you plot K power A, I of K, adjust K, then you plot this way as a function of adjust K, A, this parameter A, until you get a horizontal asymptote. This is horizontal asymptote. Horizontal asymptote. This then gives me A is equal to 1 over mu. So you determine nu that way. So you measure I of K at different angles K, and then you plot K power A, some number, which you do not know yet. Just adjust that, multiply that with I of K and plot K. You adjust, keep on adjusting A until you get a horizontal line. If you do that, then if you get a horizontal, that means this A must be 1 over nu. Okay, and this is called a Kratky plot. So yeah, for higher angles, that is K times RG larger, this is the way Kratky plot, you get the fractal dimension or size exponent. And for K times RG smaller than 1, you get, depending upon your sample, whether they are, depends on, you'll know when you make the measurements, you get a Zimm plot, right? Sometimes it's difficult to construct a Zimm plot for many reasons, right? As you experimentally, you'll figure out. But in principle, under ideal conditions, you should get a Zimm plot. In case you cannot do that, you can also get it from Guinea plot. Quite often in X-ray measurements, people use Guinea plot and Kratky plot. Since your facility is famous for synchrotron radiation, you will probably using Guinea plot and Kratky plot more often than Zimm plot. But for your samples, before you put it in your X-ray beam, it is a good practice to characterize a polymer in appropriate solutions and figure out what the molecular weight is, radius of gyration is, nature of the quality of solvent by doing light scattering. Zimm plot is suitable for light scattering. You can also do it for neutron scattering, right? For X-ray scattering, these two plots turn out to be more useful. In principle, you can also do Zimm plot with X-rays, but that's hard because of the incident wavelength and scattering angle you can have. So this is the way we are going to characterize dilute solutions. Okay. And I think this is a good place that I can stop. We can take, before I launch into the next subtopic, we can all take a break. How about that?
Hi, Professor. Now we will have 5 minutes break.
Yeah, let's do that. Thank you.
对，大家好，就是有什么问题大家尽管问，我可以帮大家翻译也可以。就是如果觉得用英语问不顺畅的话，因为那个穆素教授觉得还是大家问问题，希望大家能踊跃问问题吧。然后就是他会感觉对他的课程进行了一个思考这样的。所以没事儿，如果问的话，如果用汉语问，如果觉得英语问不习惯，用汉语问也可以的。行。我们继续考。
Just get a horizontal.
Okay. 意思是它像画
10年。Q 值对 Q。我们总结过就是 U sex sex 和 Y sex， 这个 U sex 这一个是不是叫 winner plot？
就是它到底是什么纳米平方来的？一单位是？
对吧？
你如果是纳米平方的话，大于1很远。
对啊。
如果你是什么厘米啊，那你不是上。
就 Q 值嘛 ，Q 值耳机大概0.21。
Q 值是对它是无量高度。
不是无量，这个是大米的对称高。
它就是纳米。
对啊，它是纳米。
它是纳米平方。
纳米对称高。
那就是没了吗？
对啊，对啊，所以大于等于大于
它是无量高度。
小空间10个内容。小于就是 U sex 和 sex 什么。
Are you ready?
Yeah, we are ready.
Okay. Okay, so what I have done so far is, right here I have dilute situation, dilute. So I have one chain in here and another chain is somewhere here. Okay, and that's what we have discussed so far. Now let's see what happens if I were to increase a polymer concentration even more. So I want to increase polymer concentration. You will reach a point when I keep on adding more and more polymer chains, I'll keep on, right? When I do this, I'll get into a situation somewhere here at which the chains are going to begin to touch each other and interpenetrate. So I may have one chain like this, another one maybe like that, another one maybe something like this, another one maybe like this, and on and on. There's something like this, right? And then they're just beginning to interpenetrate. And then we keep on increasing the concentration even more. Suppose I go somewhere here, right? And they will be completely intermingled. So your one chain may be looking like this, and another one would be like that. And you know, you can draw anything like this, right? And then something like this, something like that, something like this, right? You know, on and on. So what we will call is, we'll call this region to be dilute and this region to be semi-dilute. And this region to be concentrated. And this is, of course, a dilute. So we will think in terms of 3 regions of concentration. Okay. Now the question is, how do we denote the distinction between a dilute region and semi-dilute region? So that concentration at which we can depict a transition from dilute to semi-dilute, that is given by what we'll call this to be overlap concentration. Because once the chains begin to overlap, then they will interpenetrate. When you increase more, if the polymer chain concentration is higher than the overlap concentration, I will get into semi-dilute condition. So let me give a special symbol for this overlap concentration, which I'm going to write to be C star. And the question now is, how do we determine C star? How do we estimate? It's impossible to determine exactly because as you know, the polymer chains are highly fluctuating objects, right? These are not like rigid marbles, right? Therefore, it's very difficult to precisely determine C star, but we can estimate it. The way we estimate the overlap concentrations are following. Let's imagine, with an imagination, a box. Box means a volume. And while I have these chains alone, and I'll have one chain on here, say for example, that's one chain. And another chain is somewhere here. And when I keep on adding them, there will be a situation where I have something like this, right? Go on and on like this, like that, like that. So at the overlap concentration, right? At the overlap concentration, now the volume of the whole system, volume is equal to number of chains. This is the number of chains. Little n is the number of chains. Number of chains times Rg cubed, right? So let me put this way, proportional to, no prefactors, right? Rg is the same Rg that we had, depending upon whatever conditions we had. This is our starting point. Whatever condition we had, right? Depending upon, independent of chemical details, solvent conditions, temperature, independent of all those things, we know what Rg is. Rg is proportional to n power nu with all the things that we talked about in the last lectures, last 4 lectures, if you like, right? So for given any system, in general, we will have Rg. So at this concentration, at overlap concentration, right? This is at C star. C is equal to C star. When the polymer concentration is overlap concentration, the volume is proportional to number of chains times Rg cubed. That's a kind of geometrical constraint. They're just about to touch. If I add more polymers, then they'll intermingle to give me semi-dilute. If I have less polymers, I'll have this situation. So therefore, there's a very good earmark, very good mark for describing the transition from diluted to semi-dilute condition. So let's calculate C star. At this concentration, C star is equal to, let's do this, right? The volume is V, right? The volume is V at overlap concentration, right? Which is this number. We already did this, right? Okay. Volume is n times Rg cubed. Proportional to volume, right? N times Rg cubed. And the numerator, what we have? A total concentration, total number of monomers, right? That is number of chains, right? Times, let's say, Kuhn lengths, n, number of Kuhn segments. Or you can put molecular weight if you like. You can, as I told you, capital N and capital M, they go interchangeably in our discussion. So this is the total number of monomers. This is the volume. then what you get is this n gets cancelled out, little n gets cancelled out, and therefore I get this going like n power 1 in the numerator, n power 1. Here Rg goes like n power nu. Therefore Rg cubed goes like n power 3 nu. So therefore I get minus 3 nu. Okay. So the overlap concentration depends on molecular weight. And the size exponent denotes the quality of the solution under different conditions. And there is also prefactor, which I'm not writing here. Many of the books don't write the prefactors, but you can write the prefactors because we derived explicit expressions for that prefactor. Going back to our earlier notes, we know that. For good solution, what is that number? For good solution, as you know, the extra volume parameter V power 1/5, you know that. And for different conditions, you'll have different numbers. So using those things, we can also get the prefactor, the numerical number in here. But in terms of the molecular weight dependence, C star will depend on molecular weight power 1 minus 3 nu. Okay, so this is an important relation, right? I like you to remember this. This will come again and again. N power 1 minus 3 nu. This box equation you should remember or derive it. Okay. So that is the line of demarcation between dilute and semi-dilute. How about this? How about this quantity? How does one describe semi-dilute to concentrated? Right? And this is not in the books, but let me tell you, and I will not elaborate because it can become technically complicated. So I'm not going to talk about it, but in general, what I would say is line, this one, let me call to be, say, C prime or the C double star. Let me write C double star, use a different symbol. Oops. Right, this number, that is a C double star. C double star, here is my C double star. And here is my concentration, C going this way. In this region, here is overlap concentration. In the semi-dilute region, right, the density fluctuations are strong. I'm going to write it here. Strong fluctuations, strong concentration fluctuations. As you can see, there is lots of room for these monomers to move around in semi-dilute condition. But in an extremely tight melt condition, extremely constant solution, they are not able to fluctuate that much. So in this region, we have weak concentration fluctuations. Okay, that's the distinction between semi-dilute and concentrated. Quite often what we'll do is we will not worry too much about this distinction in these lectures because that becomes a subtle issue in terms of interpreting scattering data. But here what we'll do is we are going to talk about the transition from dilute to semi-dilute, and the overlap concentration is an important quantity because that's going to distinguish between whether we are in dilute solution or in semi-dilute solution. Okay? Now let's proceed further to describe the semi-dilute condition. When we look at semi-dilute conditions, there's an important concept that has to be appreciated. So if I have a chain like this, right, for example, and there is an extra volume interaction, single chain, and for that we had Rg going like n to the 3 nu, n to the nu, or 3/5, n to the nu. Let's say, to be specific, in a good solution, let me say it's a 3/5, for example. Okay, in dilute solutions. In dilute solutions. Okay. Now, when I add more and more polymers, then what happens is I'll have another chain which may come in here, like that. And another chain may come in there, like that. The result of this is the following. The intra-chain interaction I had, this is intra-chain extra volume interaction, that is getting screened. This leads to screening of intra-chain excluded volume interaction. Right? This leads to screening of extra volume interaction. What does that mean? If this monomer does not interact with this because another chain is interfering, there is no, in a dilute solutions, we remember we did the Flory theory, right? And that's how we got this 3/5 power. But now, due to interpenetration by other chains, this monomer cannot interact with this. Therefore, this will look like a Gaussian chain. Because if there is no interaction, as you know, then you get a Gaussian chain result. Therefore, this will lead to Rg now going like square root of n. It's a good solution, right? The solvent is a good solvent where we have n power 3/5 in dilute solution. But once you get into a concentration higher than C star, I'll have screening. Therefore, what I expect is this. Suppose I plot Rg versus polymer concentration. Here is my C star. Below C star, I'll have this quantity. I'll have this quantity where this goes like n to the 3/5 in this example. In other example, it will become something different. And then when the chains interpenetrate, the size will become small because now we are expecting it goes like square root of n. Therefore, what will happen is this curve will come down. It will come down like here in this region, it will go like square root of n. This is what we would expect. The radius of gyration would be in a good solvent, n power 3/5. In the same good solvent, when you increase the concentration, the radius of gyration will become Gaussian-like. That means that the chain statistics will be Gaussian in high concentrations or in melt. In a polymer melt, this will adopt, although it's a good solution conditions, roughly speaking, right? In the melt, I suppose I have a little bit of solvent, right? Still, I'll get into the half. Okay, this is a very important concept. This was not intuitively obvious, right? And the people who solved this problem, where there were two people, one person was Paul Flory. He did not solve the problem. He made a conjecture. He made an assumption that when you increase the polymer concentration, polymer will become ideal chain, although the solvent is good. And the actual proof of this conjecture came from Sam Edwards in 1960s. Right? And this is an important conceptual breakthrough in understanding polymer physics, screening of external volume interaction. Okay. Now, I need to provide you support, experimental support. Okay, because the mathematics of this proof is technical, so we don't need to worry about it today. You can always look at other publications, but I like to convince you that this idea of extra volume screening is real by making measurements and showing what people have found out. Okay, so let me go and show some experimental data. Okay, this is given to you already, right? This is a PDF file I sent you. Okay, let me focus on one picture here, and the references are given here at the bottom. Right here, there are the references. You can please go and look at those original references. So now let me look at measurement of radius gyration. This is a good solvent, right? This is concentration gram per cc. And look at this. This is in this unit C star. Overlap concentration somewhere very close here. You cannot even, because C star you cannot measure it. So this is the radius gyration, right? And it obeys the 3/5 power law. And then at a higher concentrations, it becomes Gaussian chain like. Right? It becomes like a 9 nanometers. This is RG. It becomes about 8 nanometers. Look at the original paper for details. And it goes from like 14 nanometers to 8 nanometers. It shrinks as a function of concentration. Now, this is from neutron scattering measurements. Okay. Now let me look at the Zimm plot for this. This is a melt. Okay. This is a melt. This is neutron scattering. They took a melt and they deuterated some of them. Deuterated some of those polymers. Although it's a melt, since the contrast with the deuterated polymer is higher than the protonated polymer, you can look at the radius gyration and second virial coefficient of the deuterated polymer. Since the deuterated polymer concentration is low, this is more like a dilute solution. For all practical purposes, theoretical purposes, this is like a dilute solution, although it's a melt. It's a dilute solution of deuterated polymers, right? And here the axes are in a different way. They oriented this figure differently from the way I did. So here, Q is equal to 0, that's K is equal to 0. Look at the slope here. These are different concentrations. They are extrapolating, right? These are different concentrations, different one. These are different angles, Q square, different angles. Remember, I told you this capital A, some number there, that is this 10 in their plot. But please, important thing to notice is Q is equal to 0, right? The slope should be A2. This slope is A2. And that slope is 0. So A2 is 0. Second virial coefficient A2 is 0 means ideal chain because there is no interaction at all. So in the melt, the deuterated polymers are completely miscible with the protonated polymers. Second virial coefficient 0. That means it is Gaussian chain statistics. It's obeying Gaussian chain statistics. In melt, they are ideal, behaving like ideal chains. Although this was made from a good solution. And then if you look at this slope, you get RG. So this will give me RG. That RG is this number. That RG is that number. It's a Gaussian chain. So it is a very direct proof. Right. Now let me look at additional proof in terms of this molecular weight dependence. They are plotting the Gaussian chain value, right? RG squared by molecular weight square root. So if it's a Gaussian chain, this should be a number. RG squared by molecular weight. RG is proportional to molecular weight. RG squared is proportional to molecular weight. Therefore, if you take this ratio, it should be as constant if it's a Gaussian chain. But in dilute solutions, right, that is in this limit, if you measure that quantity versus molecular weight, it depends on molecular weight. Okay, and again, from that slope, you can get that the nu is equal to 3/5. Because this is RG squared by M, square root of that is right. And then you get this is a 0.2, 0.1 slope, right? That should be square root. That's a 0.1 slope, right? So from this, we can get nu. From this, you can get nu is equal to 3/5. Size extension, that's in good solution. You make the same measurement at higher concentrations. right? If you do that, then nu is equal to half because you get this flat. And similarly, you take a same polymer, but in a theta solvent, a dilute solution, a theta solvent, then you get same data, a flat number. Therefore, this is a very direct proof of screening of extra volume interaction. So this is, I call it experimental verification of extra volume screening concept. Okay. So you have to believe in this. There is no doubt about screening of extra volume interaction. And we have to use this idea again and again and again in understanding higher concentrations. When you go to higher concentration, although it's a good solvent, when you go to higher concentration, extra volume interaction is going to be screened. Okay. So what I like to say is, I like to be confident to say, we verified this. This idea is a good idea. Okay. Now I'm going to implement this idea to extract more information. Okay, so let me look at semi-dilute solution, and I want to look at osmotic pressure. Osmotic pressure of semi-dilute solution. So what I'm doing is, right, instead of having a situation like this, the dilute, I go in here. Like that. This is my semi-dilute condition. And here I know what the osmotic pressure is. You remember this? Osmotic pressure by kT is equal to, going back to your previous case, C. Let me write C by N. That's good enough. C by N. Right? And then we had 1 plus A2. No, I made a mistake. Let me rewrite it here. C by N plus A2 C squared. That's what we did. So I can rewrite this to be C by N, right? 1 plus N times A2C plus etc. I can do that, right? Same thing. C by N, and the one factor C goes here, C squared, N cancels with that N, so I get this quantity. But I also know that A2, we work it out. A2 is equal to N power, do you guys remember? 3 nu minus 2. So going back here. A2, capital A2 is molecular weight for 3 nu minus 2. And M and N are interchangeable in our notation, right? We are using the same notation. So I go back here, the A2 is equal to N for 3 nu minus 2. So therefore, what I get here is, in dilute solutions, C by N, 1 plus some quantity which goes like, let me put a different symbol here, green. Some quantity that goes like N power 3 nu minus 1. C plus etc. Right? There's a factor of N that cancels minus one sign here. Therefore, I have N to the 3 nu minus 1 and then C. Then you can also show, if you do this again, if I go and do this next calculation, I can show then N power 3 nu minus 1 C square again plus etc. If I repeat this calculation as a series, if I go to the second virial coefficient, I get this. When I do the third virial coefficient, I will get that. Right. So therefore, this already suggests to me, that it goes like a C over M times some function I do not know these numbers, right? That's specific to the particular system. I do not know the prefactor here, prefactor here. It looks like it is a function of, right, n to the 3 nu, n to the 3 nu minus 1 times the c. Okay. By looking at our high school osmotic pressure, our high school pressure equation of state for a gas, we can very quickly come to this conclusion, right? Osmotic pressure for polymer solutions is like the pressure in a gaseous state. You know, you do this calculation, you get this one. But this is very provocative, very, very exciting. You know why? I have seen this green character before, right? Remember, this is C. C is concentration, right? And any function, the argument should not have any dimension. So this is a concentration. This must be reciprocal of a concentration, right, in terms of dimension. But I know this number. I have seen this character before. Where did I see this character? I saw that character right here. I saw that character, n power 1 minus 3 nu, is my overlap concentration, right? N to the 1 minus 3 nu. Therefore, n to the 3 nu minus 1 will be 1 over overlap concentration. So I go back here, n to the 3 nu minus 1. So I could rewrite this expression to be is equal to C by n, some function of C divided by C star. Where C star is equal to n to the 1 minus 3. In general, I can write this to be in general. I have not talked about semi-dilute solutions at all yet, right? I'm just reminding myself, even in a dilute solution, it always turns out to be this way. It turns out every quantity that we are going to talk about would be whatever we know in dilute solution limit, extremely, that is when C becomes 0, we know that limit. We know in this case it's C over N. And then everything else will be a function of C by C star. Therefore, I'm going to write this to be in general. In general, this is going to happen. Okay. Okay, given this result, we are going to do an important calculation. Given this result, we are going to do a very important calculation. Okay. The calculation is this. We look at the problem and we don't rush, do not go to a computer right away, right? We do not go to a simulation. We do not, we just take a break and think about it. In a dilute solutions, I have the polymer chains behaving independently or interacting a little bit, but they're contributing to the osmotic pressure. When I go in here in a semi-dilute condition, okay, in general, I know this is a functional form for osmotic pressure, right? I know in dilute solutions, it is C over N, infinitely dilute solution C over N, I know that. Now I need to have some expectation about what will happen to the system if this argument is large. That means C is higher than C star, because that's what we are interested in. In semi-dilute conditions, C is higher than C star. What will happen if C is higher than C star? Now let's think about this. I want you to, since I have a pen in my hand, I can draw a picture like this. Imagine I have one chain like this, another chain like this, okay? So I have two chains. I have two chains of each, say, 500 monomers, okay? Now I'm going to draw a 250 monomers chain, but 4 of them. Okay, I'm going to draw 4 of them. So instead of drawing, I stop there. That's one chain. This is another chain. And then this is my third chain. And this is my, this is my fourth chain, something like this. Okay. I cannot tell the difference. right? Here I have 4 chains, 4 chains of each 250 monomers. The thermodynamic property would be very similar, not would be identical. Therefore, what I do is I expect, this is expectation, right? I expect osmotic pressure for C greater than C star to be independent of N, but dependent on C, monomer concentration. We only care about monomer concentration, not the chain length. Because once they interpenetrate, you know, the thermodynamic property will be the same. Therefore, what I have is I have the following 3 results, 3 important results. Right. One, I know osmotic pressure by kT is in general is equal to C over N times some function of C by C star. Right? That is same as C over N in this particular case, some function of C to the N. C star is, right, 1 over 3 nu minus 1. So this is 3 nu minus 1. I know that in general. Second thing I know is for C much less than C star, right, osmotic pressure by kT is equal to C over N. I know that. That means this F goes to 1. Right? That quantity F of X goes to 1, where X is the C times N to the 3 nu minus 1. All right, I'm just copying this. Right? C star is equal to 1 over 3 nu minus 1. 1 over C star is N to the 3 nu minus 1. I'm just copying that. Number 3 is I expect pi by kT is independent of n power 0. I expect that because of this intuitive argument, or there are some general principles for this, right? N power 0. So what I'm going to do is, knowing these 3 remarks, 1, 2, 3, I can tell what this function is going to be. If I know, now given that statement, knowing this and knowing this, I can tell what that is. And you can also probably guess it, right? Because on the left-hand side, therefore, for C greater than C star, on the left-hand side, what do I have? I have C over N, and have this quantity, some function here. On the other hand, right-hand side, it must be n power 0. On the right-hand side, it is n power 0 for C. This is, you expect this for C greater than C star. On the right-hand side, it's n power 0, that is independent of n. On the left hand, C power n times this function. This function depends upon this argument. And the n, if I look at matching the powers of n, one factor of n is in the denominator here, the n power 0 is here. I can get n power 0 on the right-hand side only if this function goes like n, because in the denominator I have factor of capital N. Only if this function is factor of n, then I'll have a factor of n in the denominator, then I have n power 0. The only way that can happen is this is an exponent. That is, I will write this to be in a different notation. I write that to be C n power 3 nu minus 1 power some exponent. Only if that's an exponent, a power, I can have a factor of n. If I want to have n out of this group of terms, only way that can happen is this is a power. And you know, you can by just looking at it, you can know y is equal to 1 divided by 3 nu minus 1. When y is equal to 1 over 3 nu minus 1, that will cancel with this. That will give me a factor of n. Therefore, y is equal to 1 divided by 3 nu minus 1. By just inspection, you can do that. Only if y is equal to 1 over 3 nu minus 1, you will get this factor of n here. 1 over 3 nu minus 1, that will cancel with 3 nu minus 1. That gives me factor of n. That kills this factor of n. And then I get n equal to 0. So I have determined the exponent y. This also means, and importantly, this also tells me the concentration dependence. Using this, I can get osmotic pressure over kT in this limit is going to, osmotic pressure in this limit will be equal to C, one factor of C here, and then here you have C power, okay, 1 plus this quantity that you had y. Right? I have determined y, C power y there, C power 1. The osmotic pressure will go like C power 1 plus y, but I know what y is. Therefore, this goes like, concentration power, add y, 1 plus y. Now you can do that. That gives me 3 nu divided by 3 nu minus 1. We have managed to make a remarkable achievement, remarkable progress in making prediction for the osmotic pressure in semi-dilute solution, right, as a function of concentration. And all depends upon nu, depends upon the size exponent nu. And what is nu? That depends on your system. That's our first statement. This is our first statement. Once we know this, we establish this with the using Zimm plot, Kratky plot, or whatever, you know, any plot, the Guinea plot, you establish that, right? Once you know that, you are able to make a huge progress and then say something about osmotic pressure and all other quantities in the solution. Okay, so let me rewrite this again. Osmotic pressure by kT goes like, in dilute solution, C is less than C star, it goes like C over N. For C greater than C star, it goes like C to the 3 nu divided by 3 nu minus 1. For good solutions, nu is equal to 3/5. Therefore, osmotic pressure goes like concentration power, tell me, 3/5, right? 3 times 3/5, 9/5. 3 nu minus 1 is 4/5. This is 9 over 4. That is C power 2.25 for C greater than C star. Okay. Therefore, if I had, for example, therefore, if I plot pi over C, will go like C power 5/4. If I plot logarithm of pi over C versus the logarithm of C, I'll get a slope of 5/4. In dilute solutions, I'll have this result. Below C star, I'll have this result. Because pi goes like C, right? In a very dilute solutions, pi over C will be 1 over N. So it will go like this, there will be something like this. This is 5/4. Somewhere here is your C star, logarithm of C star. So that's a prediction from this argument. Okay, that's the prediction. Now let's see whether this is right. Okay, because I am of course I'm a theorist, but I'm also an experimentalist. The proof is coming from experiments. We can always make arguments, but we have to find validation. We have to get the experiments done to make sure the ideas are right. Okay. Let me show you experimental proof for this. There. Oops, sorry. I don't know what's going on. Okay. So this is from a book from Sujita. He has compiled a lot of data here. Look at this. Look at the data points. How many data points are there? This is the way polymer physics is done. Okay, that's why they get into textbooks, right? So they are plotting C by C star, right? Plotting versus pi over C, pi times M divided by C KT, right? Because you know the ideal law, for concentration very below, much below C star is osmotic pressure C over M. So they are plotting pi over KT, M over C. So that should be 1. Logarithm of 1 is 0. Here C is equal to C star, logarithm of 1 is 0. So this is the dilute solution and this is semi-dilute solution. Okay, so this is the dilute, this is semi-dilute. This is in the handout that I gave you. Here, the slope turns out to be 1.33. The slope is 1.3. We expected 1.25 for a good solution. And in fact, this should be, right, 1 over 3 nu minus 1. This slope will be 1 over 3 nu minus 1, as we derived. And the nu instead of 0.6, if it's something like a 0.58, 0.59, 0.59, then you'll get 1.33. Okay, this is really fantastic. So this is a proof, direct proof of our arguments. This is right. Okay. So that's exactly the proof that we had. So I'm going to now say, I'm going to draw a line in here with a big tick mark. We got it right. So what I like to do is, I want you to do this as an exercise. All right. I think we have only 4 more minutes. I do not want to start another derivation of this type because we will not have enough time to finish that calculation. When we meet in the next class, we will go through 2 such calculations. What I want to do is, I like to talk about 2 things. Suppose I have this situation, and I like to talk about what is mesh size. Now it looks like a mesh size. What is the correlation length? Because over certain distance, the monomer concentration is correlated. I like to talk about correlation length. But this is important because remember I told you long time back that weak fluctuation and strong fluctuation. What is a measure of a weak fluctuation, strong fluctuation? If the correlation length is long, then it's strong fluctuation. If the correlation is short, it's a weak fluctuation, right? Therefore, we need to understand how to measure it, of course, and how to predict. How does it depend upon the concentration? That's number 1. The other thing that I want to do is, I want to take one of these chains. Okay, one of these chains. Let me take this chain. Let me take this chain as an example. I don't know which one. Let me take this chain. I label this chain. And I like to say something about the concentration dependence of radius of gyration, because I already showed you research like this. In the terms of the screening concept, I told you there is a screening concept. Then RG goes like this. In the melt, it will be ideal. And in an infinitely dilute solution, it's a good solution. Then I have the Fourier exponent. What is the concentration dependence in here? And because I showed you some experimental data, I showed some experimental data here. Here, I showed an experimental data here. How do I define this crossover? Here it's a Gaussian chain, here it's a good solvent. How does it depend on concentration? These are the 2 things that I'm going to calculate in the next lecture. Okay. But if you have time, please, you are welcome to go into the handout and read them, be ready. Okay, I think I'm going to stop here, and I will request you if you have